Uh, Good morning, everyone. Welcome to the NASA Sea Level Rise seminar. We're very glad to have Brett Buzzanga. He's a postdoctoral fellow at the NASA Jet Propulsion Laboratory, and as a member of the Sea Level and Ice Group, he uses satellite observations of the ocean and land to understand how climate and geophysical processes vary in space and time. And he's more generally interested in the interface between science and society. He earned his MS in Earth Science and PhD in Oceanography from Old Dominion University in Virginia. And he'll be speaking today on the topic sea level along the US Atlantic coast, new observations and implications. Welcome, Brett.
All right, thanks for the introduction and the invitation, Patrick. And thanks everyone for coming. Okay, hopefully you can see my screen. Play. Okay, let me just move you guys over here. All right, so yeah, thanks for that introduction. Just to add a little bit more general statement, I think you're going to hear through this talk that, like many people at JPL, I'm sort of at this interface between science and engineering, and it's kind of a unique place we have at JPL, and it's hopefully it comes kind of clear as I go through some of the new data that we're making and trying to show the community, as well as some of the questions that we're kind of beginning to ask of it. And you can also see that I have this really general title here. Of course, that's deliberate, as I'm going to be covering quite some different areas, all related to sea level in one aspect or another, but I think I may have some of you confused and some of you bored at different times, but there will be plenty of time, I think, for questions at the end. So let's get right into it. I'll start with just a couple introductory slides, just very quickly. This is a sea level seminar. We all know these. Obviously, global sea level rise has been going up for about at a rate of about 3.3 millimeters per year. A lot of this is a direct climate indicator, as anthropogenic warming has led to excess heat that has warmed the ocean. And of course, we also have direct societal impacts, chiefly related to flooding. And we know that this 3 millimeter rise isn't spatially uniform. There's lots of different areas experiencing different sea level, with areas like the tropical Pacific experiencing a little bit lower sea level rise rates over the last 30 years or so, and areas like the US East Coast experiencing much faster rise. And we have a couple different ways of measuring this. We know this from tide gauges, in situ instruments, which have been in some cases recording since the turn of the century, and even longer in some cases. So I have this nice example down here in the bottom left. There's a tide gauge hiding in this Monet painting from 1890, and it was just this flagstaff that would bob in the water with the tide, and obviously wasn't recording any data, I don't think, but probably pretty useful for these little boats to get in and out. And now we have, of course, the radar ones over here, and this yellow one. I'm not sure if you can see my mouse or not. And then, of course, the last 30 years, we have the satellite radar altimetry records that have monitoring the Earth's surface or oceans near globally. But one really important area that we kind of miss with kind of both these instruments is this near shore coastal band, this really within 25 kilometers of the coast. You can kind of see that here illustrated by the actual ground footprint of the satellite radar altimeter. You have about 300 kilometers between tracks. And as you get close to land, you have the footprint kind of gets contaminated, and the wave models that we use to relate the waveform back to the satellite get kind of corrupted. And of course, tide gauges, they're not everywhere. There's definitely variability in between them that are missed. And of course, a little bit further away from the coast, it's kind of hard to see with those. So we've begun exploring some new data from ISAT-2, specifically LiDAR data, that can be used potentially to fill this coastal gap. And of course, this was designed for the cryosphere, but it is covering the whole Earth, and has a bit slower repeat time, 3 months relative to the 10 days or so of the radar altimeters. But that's the expense you kind of pay for this really fine footprint. So here's the structure of the satellite over on the left-hand side here. You have these 3 pairs of beams, and each of these pairs is 90 meters apart. And each beam itself is about 15 meters. And then the along track direction, we have about an effective footprint of about a kilometer due to different adaptive averaging, essentially. And you can kind of see this a little bit better illustrated here. So here is just New York City. I'm not sure how many of you are, I guess, or nearby, but I tried to choose a few local examples. And so here are the tide gauges marked as stars, and you have the radar altimeter from JSON3 are these green lines here. And if we add ISAT2, you can kind of see a lot of this get filled in here. And this really isn't a dramatic example. This is actually a not dramatic example, but I wanted to again show something local. And this is great, we have this data, but is any good? And to be honest, and pardon my French, it is pretty damn good. So here are 2 years of data, just from 2018 to 2020 in the early years of the satellite. And on top, you have the record from JSON3, and on the bottom, ISAT2. And as you can see, all these kind of gaps, these kind of white marks in the top area are really nicely filled in the ISAT2 on the bottom. And we have this great basin scale agreement. You have this La Nina in the tropics over here, and also have this Indian Ocean dipole event. I think I circled them for you, that are really popping out really clearly in both of these maps. And we do see some high variance, especially over in high variance areas like the Gulf Stream, where there's lots of eddying currents, and this does add some noise, a lot of noise to the ISAT2. But this is just 2 years of data. We add 2 more years of data, you can really see these noise levels come down. You can see kind of these reversals also, and again, that Indian Ocean dipole and the La Nina eases a little bit. You kind of just flip back and forth a few times to kind of see this difference here, and these the magnitude and just kind of the noise reduction as we get a couple more years of data. And so we can look at these differences more formally by actually computing the differences at each grid cell throughout the globe. So I've just taken literally the difference of ISAT2 and JSON3 at 3 different grid sizes. And then you can see the box plots here. They're all pretty close to 0, as we would hope. There is a bit of a bias of about 3 millimeters, with ISAT2 being a little bit higher. So this might be a C-state bias correction issue. We're still looking into this. If anyone has any ideas, welcome to share them. But of course, this is the open ocean. We really are kind of more interested in the coast. And so here, what I've done is I've compared both the altimeters to tide gauges along the coast. And again, I'm showing the difference. So the lighter colors are going to be the ones that we would hope to see. And again, you can see if you kind of just look generally, you don't see anything too different between the two. JSON3 does quite a good job, as we would expect, and know from decades of observations, especially along like the US East Coast here and the US West Coast. And there's not really too big of differences between the two. And you can kind of see that a little bit more formally here. So on the bottom, I've shown in green where the JSON3 does better in quotation marks, and ISAT, whereas with the blue shows where ISAT2 is better in terms of its difference with the tide gauge. And so again, there's kind of this more or less an even distribution. And if we look on top, we do kind of see that ISAT2 is picking up a lot more. There's of course just more data near the coast. We can get a lot more comparisons over this time frame with tide gauges. And you can see this illustrated pretty clearly in Australia. And here I'll pause and just say, I put the word better in quotes, and I'm using this word better in not really a good way, because I'm not trying to say that one sensor is better than the other. Really, they both have different strengths and weaknesses in different areas and different time scales. And it's really about, I think, using these observations together along with the in situ instruments to get a better understanding of coastal sea level as we move forward. And hopefully we can illustrate that a little bit if we look at perhaps an ungauged coast, or at least a poorly gauged coast. So this is this giant coastline of South America. And we have only these 5 or 6 tide gauges, these white stars I've marked. And here's the JSON3 in a 1/4 degree grid. It might be a 1/2 degree grid, I forget. And you can kind of see these features start to pop out. You see these elevated rates over in the northern portion of the map, and you see this interesting kind of dipole thing going on down near Buenos Aires where the gauges are. If we add in the ISAT2, now you can really start to see, oh yeah, we clearly have this elevated patch of sea level rise up in the northern portion, and there is this really interesting dipole kind of banding pattern down here, which I'm not sure what's causing it, but I'm guessing the tide gauges are right where this more or less is. So someone must know about this, and yeah, would like to hear if anyone knows why that happens as well. But even if we move to a heavily gauged coast, so here's the US East Coast, again, the tide gauges. You can see the JSON3 and again, the ISAT2 comparison here. And let's just blur them a little bit, squint a little bit at them to help us see some of these features pop out. So here is the measures. So this is an aggregation and interpolation of basically all the radar altimeters that are up and have been up. So this goes back to 1993. And it's a product produced by JPL. And here I've just applied a Gaussian blurring to ISAT, just kind of get a better overview of what's happening here. And again, we can see some really nice large scale agreement. So here's the Gulf Stream popping out really clearly in both of these figures and the North Atlantic extension. But we also see some differences. And so, for example, over in the Chesapeake Bay, here you have some more elevated rates that we're seeing in the ISAT. And if you look over in the measures product in the same kind of region, you see either flat or maybe even some negative rates. And so this is kind of where we think, okay, maybe this is that problem with the coastal footprint of the radar altimeters impacting these trends, or maybe there's too much noise in the ISAT. We have to dig in a little bit more, kind of disentangle these differences. But it does give us a good clue on how to proceed forward. But, rates are one thing. I've just been showing linear trends over these time periods, which I hope I made clear. But if we look at the time series themselves and start to think a little bit more about what we're seeing through time, we can start by looking at the standard deviation, essentially, in these two different products here. And again, we see some pretty nice agreement, especially we're capturing this high variance as the Gulf Stream kind of breaks off here, and eddies and does all its fun stuff. We also have this huge patch of noise essentially down in the Caribbean. I think this is going to be due to most of these islands are not getting properly masked out. It's partially my fault. I can do that a little bit better. But we do see these nice patches of agreement. And let's look at this extension, North Atlantic extension over here. Look at the time series itself, and again, I've just fit here a simple linear plus seasonal trend. Again, we have this kind of nice agreement between the two. We do see some interesting discrepancies, and looks like ISAT is over, I guess, getting a little bit extra variance in these seasonal peaks. So it takes a little bit more work to figure out if this is kind of a global thing or if this is kind of just happening here. But again, it could be some sea-state bias, but a little bit more work to dig in and figure out what's happening. So these are still kind of some preliminary results. We had that paper back a couple of years ago with the first comparisons, but now it's time to really dig in and continue to push forward and see how close to the coast we can get and how well it's really doing. So it's we're going to change gears a little bit, and it's important to remember that sea level is this state variable, right? It contains tons of information on the Earth's system, particularly ice sheet, mass loss, aerodynamic changes, but it doesn't contain everything, right? It only kind of contains, we have this simplified equation for a relative sea level. We have ice, ocean, atmosphere kind of being captured by the radar and any kind of altimeter. We miss this vertical land motion component, and relative sea level is really I define it as the sea level that's experienced by the coast. So it includes this vertical land motion component. And we know that VLM is pretty important, right? So here in this map from Bill Hammond et al. A couple of years ago now, it's 2023. We have this kind of these blue colors throughout large parts of the globe, especially where people live. And the blue is indicating subsidence. So of course, where we have subsidence, we have downward motion of the land. We're going to have elevated rates of sea level rise. And this is a heavily interpolated product. It's important to keep that in mind. This is mainly from GPS measurements, and it was designed to be used at tide gauges. So it's really, they do the calculation at tide gauges along coasts and then kind of interpolate to make these larger scale maps. You can kind of see the effects of that here. So if we look at the top left, this is a close-up of Hampton Roads, and we'll look at this in a little bit more detail as we go forward with the talk. And Hampton Roads is in coastal Virginia. It's where Old Dominion University is, where I did my graduate work. And what you can see is these boxes here in the colors are the results from that imaging product. And it's dark here because there's just no data over this large area. And you can see also these GPS stations, and they're colored in by the rate here. And you can see already just from the GPS that there's quite some spatial variability, ranging from about no trend up here to 2 or 3 millimeters as you get over more south, essentially. And so it would be nice if we could look at this a little bit more closely. As you can see, the GPS stations, we do have a number of them along the coast, but there's going to be some interpolation required to if we're going to approach this from a method like this. One other thing we can do though is to look at just the large scale patterns. And so here I'm showing the same area, but for the vertical land motion from 2 different GIA models. So on the left, I6G, on the right, from Lambert-Caron's ensemble. And again, you can see that there's flat out these big difference between the two. I think it's at least 0.5 millimeter between the two, and there's of course almost no spatial variability in agreement with these GPS stations underneath. So it would be nice if we had another method to constrain these magnitudes and to kind of see if we could capture some of the spatial variability. And of course we do. We have remote sensing from InSAR. So InSAR stands for Interferometric Synthetic Aperture Radar. And essentially you have a satellite flying over the land surface. So here we're up at this glacier in the Arctic, and it is making this nice radar image at time 1. And then about 12 days later, six days in some cases, it's going to fly over the same location again, come up with a very precise radar image of this, of the land surface or glacier surface in this case. And then what you can do is you can difference the two to get a really precise estimate of vertical land motion after accounting for a number of error sources, such as the delay of the troposphere as the signal passes through. So for those of you who use radar altimetry, I always like to make this comparison. I mean, you can go online and you can download a pretty nice gridded product for anywhere in the globe from radar altimeters over the last 30 years or so. You can't do that for InSAR. There's still specialized processing that is required. There's still a number of error sources that are not well. The community hasn't settled on one method to resolve them, and there's varying ways to do that. We can talk about that more because it's a lot of my day-to-day job lately, actually. And kind of on that same track is there's a bunch of different algorithms that exist to make these interferograms, to do this calculation, and specifically to do a time series calculation, so to combine not just the displacement between 2 times, but to stack these into a network that captures essentially what you want is the full record length, at least of one satellite. So for Sentinel-1, which is the cutting edge, about 7 years since 2015 or so. And so I'm using the software called Fringe that's being developed at JPL, and I'm going to say some nonsense right now, but we can talk about it more later. And the idea with Fringe is that it kind of combines InSAR using all possible pairs in this DS, distributed scatter, persistent scatter approach. Talk about that one a little bit more. And it uses basically an eigenvalue decomposition to mitigate noise and to basically enhance the computational efficiency, because you get these huge data sets that you have to make a lot of assumptions in order to deal with just the terabytes of data that are coming in. And so let me just illustrate some of this gibberish is this DS versus PS approach here. So typically, here's what you have from a single resolution element on the ground, right? You have all these scatters that are combining into what the satellite sees, and at full resolution we have about 2 to 5 meter pixel. But this is everything from different leaves changing to mowing the grass between times, and what you can do is, and where one approach is to say, okay, well, we have these differences. They're going to be kind of homogeneous in space over small areas. So, for example, a forest is going to have similar scattering characteristics through time. So we can kind of focus our analysis on a group or a distributed group of scatters within our framework. Whereas the other philosophy wants to focus on like a single dominant scatter, single dominant, perhaps tall building, or usually it's a tall building that doesn't really change in time. That's going to give a consistent reflection back to the satellite. You kind of would focus your analysis on those ground resolution elements. But what Fringe does is it kind of takes the best of both worlds and is able to combine both these approaches. First, it defines distributed scatters, and then it defines persistent scatters and uses some kind of weighting to kind of blend them together. And what you are able to get then is these really fine scale maps of vertical land motion in different areas. And so let's kind of disentangle a few of them. So this is Hampton Roads again in coastal Virginia. This is Chesapeake Bay, is kind of up here. Atlantic Ocean is right over here. And what you're seeing here is essentially broad scale subsidence at 30 meters resolution. And the first thing you can see is that we're, of course, capturing at much finer resolution the spatial variability. So you kind of see this east-west gradient. of heavier subsidence over in the west. Now, I will say that this is a little bit more noisy, but there's definitely quite a bit of variability as we go through this region. And if you look over to the north here across the James River, there's very little subsidence down in the city of Hampton here, which is an agreement with the GPS that I showed actually previously. And so the power of this is not only do we get these kind of overview maps, we can really zoom in, right? So here's in northern Norfolk, and this is a pretty important area. This is where the naval base is, the largest naval base in the world. And you can see these two areas of really high subsidence pop out right away, that one and this one here. And this is kind of typical when we start to look at these maps in more detail. We start to see these areas, especially along the East Coast, which is primarily where I've looked, of essentially filled in marshes is what drives typically these really hot spots of subsidence. So back at the turn of the century, the previous century, settlers were building up the city, and they wanted to fill in these kind of marshy, soggy sediments and build on top of them. So they kind of threw shells, they threw whatever they had. Oyster shells is a big one that I've heard to just fill in. And of course, over time, these buildings on top of them are settling, and we can see that in these kind of these hot spots of subsidence. And it's interesting. Moving forward, we're starting to make these maps, and we really are starting to try and figure out with stakeholders and practitioners and regions how they can use them and how they can be useful. And I think the community is still trying to figure all this out. But thinking a little bit forward, you would want to focus on these areas that are not subsiding super fast. I think if you're kind of building coastal infrastructure to defend sea level rise, or thinking about where to further develop. So I think we're not at that point yet, and it's kind of outside the scope of this talk, but it is something to keep in the back of your mind as the community moves forward and these vertical land motion maps become more easily to produce and more familiar to people. But for now, we can look at another example. So let's go down to Charleston, South Carolina. Again, you see this broad scale subsidence start to pop out throughout the region. It's deep blue. And again, you see these hot spots of subsidence, which I've talked to a few people down there from NOAA, and they are indeed these filled in creek beds from historic times. And we can look at we can assess kind of the accuracy as we go through the region. So I've drawn this transect that starts up here at this top A in the north, and then we kind of follow that down through the region. It's going to go down through this GPS station here, and then kind of cut across. And you can see that we have this heavy black line is the median more or less, and it's about a couple millimeters of subsidence throughout the region. And you also see the uncertainties in time and space plotted as the shaded in the shading around it. And so you can see that the uncertainties are on the same level more or less as the signal. We have a signal about 2 millimeters per year. We have an uncertainty about 1.5 to 2 millimeters per year. So we're really at the edge of the signal to noise ratio of what we can kind of squeeze out of this. But as I mentioned, there's continual process in the algorithms and the noise corrections that are ongoing. And if you look down at the very right corner here at the end of this transect, we have another GPS station that was not used in this analysis, and you're able to see this really nice agreement in this yellow line here, capturing the GPS rate and uncertainty and the InSAR rate underneath. Okay.
Sorry. Yeah. We have a couple of questions in the chat.
Okay. I do see this. Are subsidence due to groundwater overdrafts? That is one of the reasons. Typically, that is usually a common reason. So especially in Hampton Roads, there's a big groundwater extraction over in this top left corner of the map. It's actually off, but that is thought to extend all the way through this region from these two paper mills that are huge extractors of groundwater. So that is definitely a cause. And Chris Little asked, how long is the period of these subsidence trends? Yes, I didn't say that. Also, my screen just went away. These are the full Sentinel record, just about. So 2015 to 2022, the end of 2022, 7 years. Okay. So now we're in New York. And again, we see similar features. We see the large scale subsidence. This is what we just, again, what we expect. There's not so much groundwater influence over here from what I understand. This, I think, is just simply, you're just simply loading the ground surface with these. Obviously, the industrialization of New York City is going to contribute to this settling. But what's really interesting are these two red blobs, very scientific term here that you see in the corner, well, sort of in the corner. And this is uplift on the order of 2.5 to 3 millimeters per year. And we really have no idea what's causing this and would love to figure it out. So if anyone has any ideas, we've done a lot of stuff to think about it. I mean, you can look at the time series. It's a pretty persistent upward trend. It's not, you know, dominated by any specific interval. Here you can also see the length of the record here, Chris. You can kind of zoom in on this area and look at what the ground surface is. I mean, it just looks like a quiet residential neighborhood in Queens to me. But here you have this strange patch of subsidence. The other one, this is the more northern one. The other one is similar. It's near a port, so maybe there's some industry at that one. Sorry, looks like there's more in the chat. I want to see if someone has an idea. Superfund sites nearby. Yes, Philip, you're the person I've been meaning to ask about this, actually. So I'm glad you're here. Volcanic activity? I don't think so. Yeah, so that's Superfund sites would be. I tried to find some things like this. Looked at the city records and some building records, and I didn't find any groundwater records, and didn't find anything specific. But yeah, Superfund would be definitely something to look into. So yeah, I think that's, yeah. So that's about all the maps I'll show you of InSAR for now. I'll just make a quick note. As I mentioned a few times now, we're kind of still we're not in early stages of InSAR, but we are in kind of this transition stage where we're going from individualized processing and like regionalized specific analysis to more global and more automated algorithms. And kind of the leader in that is this Opera project. I'm not going to read the long acronym, which is from JPL, and it's lots of NASA partners were involved in getting it, and lots of federal partners were actually involved in scoping it out and deciding what they wanted. And what was decided on was these 3 products, which are all, you know, from remote sensing analysis, which are surface water extent, so basically mapping globally, rivers, lakes, all these as fine as we can get. This is well on the way. I think there's already a beta product out for this. Surface disturbance is ongoing as well. So this is going to be mainly related to changes due to fire. But really the one of interest for this talk is the surface displacement product. And so we're producing over North America, over the entirety of North America, line of sight displacement maps at 30 meters resolution. And this is getting spun up now. The first one should be coming out in the next couple of years. And it is important to note that these are going to be in the line of sight of the satellite. They're not going to be vertical, so they will have both horizontal and vertical motion in them. So there'll be one more step, but even just having that globally is going to, I think, revolutionize both the applications and scientific communities. But yeah, so that's I think that's enough advertisement for now. So let's zoom out again. Let's zoom out back out from our kind of localized analysis of InSAR and even from vertical land motion to kind of looking at general relative sea level again over the East Coast. And so I think I've shown that we have this important spatial variability of vertical land motion on these localized scales, but really, how important is vertical land motion to relative sea level along the entirety of the Atlantic US coast? Because if we kind of think about this from a very basic point of view, what I'm showing here is the discrepancy between relative sea level along the US East Coast and the global mean. So I'm showing the global mean over the 20th century, over the whole 20th century. So it's about 1.5 millimeters per year or so, this blue line. It's from work from Fredericks et al. And if we take our tide gauges and we remove a GIA estimate, so basically a large scale vertical land motion estimate, we still have a discrepancy. We have a relative sea level rate of about 2 millimeters per year over the US East Coast versus this 1.5 here. Alternatively, if we remove vertical land motion from GPS at our tide gauges, again, we see this pretty large discrepancy, still about 2.5 millimeters versus the 1.5 or so of the global mean. So we'd like to understand what is controlling the differences, this additional rise on the US East Coast versus the global mean. I'm just going to pause. I do see some more in the chat here. better. Okay, we can go back in that. Okay. And so to get at this, we're going to start to think, we're going to basically bring in all the data that we can. And we're going to bring in relative sea level from tide gauges and GPS vertical land motion, sort of top-down constraints. But then we're going to kind of bring up bottom-up knowledge also of the processes that we know can contribute to relative sea level along the U.S. East Coast. And we can just start with this, very basic model here of relative sea level is kind of geocentric or sea surface height minus vertical land motion. And then we can break this down by adding in the contributions from specifically GIA, so glacial isostatic adjustment to the last ice age. I'm not going to dwell on these. I think most people are probably familiar with them, but we can talk about them afterwards if necessary. And also, we're going to bring in this ensemble estimate of barystatic plus gravity, rotation, deformation over the 20th century estimates from Fredericks et al., which is related to contemporary ice melt loss in the Arctic and the Antarctic, as well as mountain glaciers. And you can see here on the right, the locations that I have from all these different instrumental measurements, as well as the grid cells of these two. And we also have some paleo proxies at salt marshes that we're going to use to kind of constrain our relative sea level as well. And the idea is to bring all these data together in a probabilistic model. And this is going to be based on the work of Paikush et al. In 2018. We've taken that model and we've expanded it. And so let me give you just a brief overview of what's happening with this model. So that the idea kind of is that you have this hierarchy of levels. And at the base level, more or less, you have the actual geophysical processes of relative sea level, sea surface height, and vertical land motion that are hidden, that we don't actually see. That they're continuous in time and space, and they're imperfectly sampled by our data, by our instruments. Our data are gappy, they're biased, they're noisy. So they give us some idea of these hidden processes, but it's not perfect. But we can assist our data by bringing in prior knowledge. So this is where we're going to bring in estimates of GIA and BGRD from these other model frameworks. And the idea is that we can probabilistically define every term in our equations, as well as all the parameters, all the assumptions, going down to the level of the uncertainty in the datum correction of the tide gauge, or the datum adjustment of the tide gauge, for example. And we bring all these together, all these different distributions, and we invert them with Bayes' rule. And we solve that equation, estimate the solution to that equation using Monte Carlo methods. And essentially, as you can see in this picture, we start with this kind of blurry estimate that's defined by our covariance structure of all our different processes. And then by sampling over and over again, we get kind of a best estimate that we can more clearly see. And so after we run this analysis, here are kind of the results that we can look at as a first glance. So if we move from left to right, you can see in the left-hand side, we have our total relative sea level. Excuse me. In the middle, we have our vertical land motion, which has been inverted. And then on the far right, we have a sea surface height estimate. And these are all plotted as functions of latitude. And if we move down, we can see our individual process contributions. So we start with the total, then we have the contribution from GIA, the contribution from the barystatic plus GRD, and then finally this residual term, which is kind of what's left over. And we can start with the top two rows. And we see that we can clearly see that GIA is driving the spatial variability of relative sea level. That middle panel kind of matches very nicely that one on the left. And this is not new. This is what Paikush et al. Found in 2018. And so we just confirm those results. What's new in our model is that we were able to bring this BGRD, and it is nicely constrained. The estimates from Fredericks et al. are pretty well constrained. The melt source location is uncertain, but the amount of melt is uncertain, but where that mass goes, the fingerprints are precisely calculated. And then finally, we have this residual term. And by quantifying this barystatic and GRD, it's let us have a better physical understanding of what is actually in these residual terms. And specifically, if we look at the VLM first, you can see it's more or less centered on 0. Despite what Gavin said, there's no volcanoes on the East Coast, so there's not really much tectonic activity. We wouldn't expect there to be anything left over in this residual. But in the residual sea surface height, we do have this basically a longshore trend of about 1 millimeter per year. And this we do expect to be physical. We expect it to contain maybe 3 things. One is the dynamic sea level related to ocean currents. One is the global mean thermospheric rise. And then one could be the inverted barometer effect. But previous work has shown that on a centennial timescale, so again, we're looking since 1900, on a centennial timescale, local winds as well as the inverted barometer effect are essentially negligible. So we're going to stick with just these two, dynamic sea level and the global mean thermospheric. And what we can do then is we can kind of go back to our original question, which was, what is causing the anomalous rise along the East Coast? And I've removed now that global thermospheric from the residual to give us just the sea surface height due to dynamic sea level. And if we look at these different histograms, we can see that as we expected, that this dark red curve of about 55% or so is the relative sea level due to GIA. So as expected, more or less, the GIA is really the dominant source of discrepancy driving the difference in the global mean on the East Coast. However, there's still a remaining 40% or so, 45% or so that remains unexplained by GIA. And although it's uncertain, it looks like dynamic sea level is a pretty important component of that. About 45% or so of the anomalous coastal relative sea level rise is related to this dynamic sea level. And so, of course, we understand, what causes GIA, what is then going to be causing perhaps this dynamic sea level change over this time scale. So what we can do then is we can look at the results kind of like this. So this is a bit of a confusing plot. So this is a violin plot. And what it does is it basically combines a box plot along the vertical axis. So you have your median here, as well as your quartiles marked by these dashed lines. And then we have the histogram over the entire probabilistic ensemble along this axis here. And you kind of just to show that it is normally distributed and there's nothing kind of too wonky. You get kind of a little bit of bump here, but it's more or less normal. And what we can say is that, okay, there's about, at least for this GIA prior, which was I6G, about 90% of the dynamic sea level trends were positive. And if we look across these other kind of grayed out ones, maybe I should have put them a little bit darker, but the idea is that this kind of holds for these other two models as well. And it does get a little bit lower for this more agnostic, we'll call it prior, which doesn't fit the GIA. That kind of the details of this don't really matter too much. We can talk about them later. But the idea is that if we have a majority of these coastal dynamic sea level trends greater than 0, we could think about other results that have linked coastal dynamic sea level to different processes. And one thing that could be linked to is the Atlantic Marine overturning circulation. I mean, very basic geostrophy since 1938 or 37. People have shown that the coastal dynamic sea level is related to the AMOC. And so we just want to suggest, I would say, not even suggest, but other results have shown that there's a possible 20th century slowdown. And these results have been shown using numerical models, specifically the CMIP5 ensemble of models, as well as a specific set of paleoproxies. And these have shown that these have pointed that the AMOC has slowed over the 20th century. And of course, this is dramatized and constantly in the news as a major impact of climate change, and it would be if it continues to manifest. But the historic trends are highly uncertain because you had that suite of models and that set of paleoproxies indicating a slowdown, but the newer set of CMIP models, the CMIP6 ensemble, doesn't really show a slowdown. Maybe starting in 1980 or so, it shows a slowdown that starts to occur. And if we kind of think about, there's been another paper or comment come out recently that says, well, if you consider the whole suite of paleoproxies, then maybe the AMOC actually hasn't slowed down over the 20th century. So what we're showing here is just an estimate from tide gauges, right, from sea level, not using, we have some proxies that constrain, but we're really not using any of the methods that have been employed by these other authors. It's kind of an independent data point that does seem to corroborate the idea that, well, if dynamic sea level slowed down, dynamic sea level rose, the AMOC could have slowed down, but still very tentative. But we can do one other thing with our dynamic sea level estimate, and that is we can relate it to also interior dynamic sea level. So here, instead of just looking along the coast, we're going to look at the gradient along the coast. And by taking the gradient, there are some ocean dynamical equations, relationships that can show that coastal dynamic sea level is related to interior. The gradient of the coast is related to basically what's happening on the other side of the western boundary current. And so then if we plot these again as violins, we see a much weaker trends. We see much more uncertainty, but we still generally across our GIA models, we do still see this possibly an increase in interior dynamic sea level over this time period, about maybe 60% or so, showing a positive trend. And so if we think about this in terms of circulation, well, if the interior gyre is kind of mounding up a little bit, then you would have a stronger flow essentially due to geostrophy. And so you could think of this, okay, maybe we have a kind of a faster spinning subtropical gyre. And so if we take these things together, we can look at this schematic of the North Atlantic, and we can look, okay, so here's the Gulf Stream coming across here, and we can think of this as part of the, we'll at first think of it as part of this subtropical gyre. And our results would suggest that, okay, we have this mounding, this is increasing, potential increase in the subtropical gyre from that interior trend. Meanwhile, we also have this coastal sea level rising, which would indicate this slowing of the deep western boundary current, again, by geostrophy. So we have less heat being transported northwards and less warm water being transported northwards, and more and less cold water being transported southwards, so kind of being stuck up there. And all this together could lead to, it would lead to a reduced equatorward heat transfer, right? Meaning basically you have this cold water more or less being stuck kind of around Greenland in this Labrador Sea area. And this does, of course, agree with the cold blob. You have this terrible name, or the warming hole anomaly that is pretty well known from temperature records as well as other records. And so, taking all these together, it's still tentative. It's still uncertain. I probably didn't explain it well. We're still kind of working through it. But it is just, it really speaks, I think, to the power of sea level observations and sea level and models that parameterize the processes or describe the processes, and how we can use sea level as a state variable to understand the Earth system. And so with that, I think I'm just about done. Yeah, so hopefully I've shown that ISAT2 has the capability to fill these data gaps in the radar altimetry record, and as well as the in situ measurements, and kind of complement them and really help us to understand the coastal sea level, how the variance propagates from the open ocean to the coast, and what effect that's going to have on inland communities. I think I've shown some maps of vertical land motion from InSAR. You can see this different widespread subsidence, some interesting features pop out, and this definitely exacerbating sea level rise in specific locations. And finally, that, as I just mentioned, sea level is an important tool, I think, for studying the Earth system. Many of us all know this already, that we can, there's many things we can glean from such an important state variable, including perhaps a potential decline in northward heat transport over the 20th century. And so with that, thank you for your time. I see there's some stuff in the chat, and I'm happy to take some more questions. Just screenshot in here. Can I see this? A possible clue. Okay, possible clue. I love clues. So I'm looking at this map here, New York City Department of Sanitation. I'd have to get myself situated, but I'm guessing the sanitation department could be doing something here. Is what?
I put an annotation in, but there's a place called Big Geyser right at the end. So I'm thinking, who knows?
Big Geyser. Oh, cool. Thanks. Yeah, definitely something to look at.
Well, I looked up the Superfund sites as well, and they're not quite where you said. Can you bring up your graph as well? The New York City thing.
Yes.
All right, this isn't like super. Yeah, go to the one where I can actually see what's going on. Yeah.
Yes.
Yeah. Okay.
Yeah,
so that's right at the tip of Newton Creek, right? So if you look at the first one I uploaded, like there's no Superfund sites near there. So I don't think that can be
Yeah, I mean, define near.
Well, I mean, like they'd have to be, local to that point. I mean, like the nearest Superfund sites look to be like a couple of miles away.
Yeah. I mean, it would depend on how deep if they're injecting something, for example, and how deep it would be and how far it could spread.
They can't be injecting things at an angle. They have to be injecting things directly down, right?
Yeah, but I don't know. I don't know if it could be more of a spreading feature depending on the hydrogeology, but
possible. And
yeah,
I'm trying to work out exactly where the second one is.
the northern one. Yeah, it's
yeah. I mean, where is that? That is.
It's right next to. I believe. I think you can see it here. Woodside is what I've been using as my marker. So it's like, yeah, right here.
Yeah, that's interesting.
I wonder whether someone stopped pumping water out of the ground.
Yeah, that was another thing we thought of. I saw some information that said the city stopped using groundwater, stopped, around 2007. So that was maybe too long ago. I'm not sure. And I think that was for drinking purposes. I'm not sure if there was other mandates or policies for
why it would be so blobby, though, I don't understand, because I think the stopping of groundwater was much more widespread, but that needs to be looked into detail.
I agree. Yeah. It has a widespread impact. It's causing a lot of basement flooding in South Queens. When you go toward Jamaica Bay down there's a lot of and so the uplift there in that whole wide region that's sort of yellowish blue to the southeast of those points you're looking at with the rapid rise. Yeah. That whole area, it struck me, might be due to the groundwater recharge that's been occurring over a decade or more. That's causing more and more problems. It could be leading to uplift, I imagine.
Do you think it has anything to do with the presence of those water treatment plants there? That the hydrology is being somehow has changed over the years. Anyhow, it's interesting.
I mean, it could be something that nobody knows about, right? So it could be an industrial thing where they've been pumping stuff down to get rid of waste, and they haven't told anybody they're doing it.
Yeah, I was going to suggest you look for micro seismic mapping, because that'll give you a different spatial view, but you may get some clues as to what's causing the shifting that's clearly visible.
I'm not aware of any microseismicity in that area. That's Klaus Checker.
The other. Who was the first person who spoke? Sorry. Who suggested the microseismic?
Oh, Chris Schumann down here in Greenbelt.
Okay, thanks. Yeah, I'm not familiar with this stuff. I saw an interesting, I think it was just a newspaper article about basically, what do they call them? Citizen scientists collecting seismic data and these little instruments around. And I looked where they had them, and I didn't see any too close to here. Mm-hmm. Yeah, I should probably look more formally at what could be there, even if it's small.
The issue which I was actually quite interested in here, coming from the near Baltimore, is, do you see any impacts of Army Corps of Engineer dredging activity, because they're pulling mass from one location and piling it up in another location? There should be a signal.
Yeah, we do. So you can't see it actually here, because I've masked it out because it's so noisy, but this was how we kind of verified when we first started doing this analysis. Can you see my cursor here?
Yep.
Yeah, so this is Craney Island, and it's subsiding extremely fast around the edges because they put all the dredging material here, and it's basically designed to subside. And so this is how we, in our published works, we make a big deal of talking about Craney Island and this exact feature. So we haven't looked at it specifically elsewhere as a verification tool, but it really probably should be more looked into.
In the Baltimore area, they're actually rebuilding an island that was once larger and shrank considerably over the decades. So that's another location for you to test out on.
Oh, that's cool. Thanks. I think Chris. Oh.
There was a question from Natasha in the chat a little bit earlier.
Yeah. Is there a correlation with with sea level rise trends in the North Atlantic? Yes. Is Tal here? And I saw him here earlier. Tal's done a lot of this work. I think he can speak to that in better than I can. I'll just say that another question that has come up is how well does the MoCA rapid trend correlate? Basically, what's the trend in the rapid MoCA array, and that is uncertain because it keeps kind of reversing. So there's no real long-term trend, at least over the 20 years or so that would suggest that an AMOC slowdown. It's a little bit different question than you asked. But
it's a negative trend, but it's not quite at the 2 sigmas.
Okay. Yeah.
But it's not that it's like flip-flopping every year. I mean, it's been.
Yeah. I think when the first one came out. Like that, but. Yeah, that's fair. And then I think Chris had an interesting question here too. Can you talk more about the nature of the coastal dynamic sea level gradient trend? Is it uniform along the coast from where to where? Okay, so
I think looking back at that figure would help with the individual components.
This one?
I think it's that residual SSH deviation from a uniform is what you're calling the gradient.
The gradient is in space across latitude, and it is dominated by up in the northern portion here,
where it's lower than the spatial mean.
No.
I don't know. That was a kind of a question. That was meant to be a question. Like, what is the nature of the trend? Is it lower to the north, higher to the south? And
it is higher. It's higher to the north.
Higher to the north. Okay.
But yeah, this actually just came up. And this result just changed recently a little bit, so I have to recalculate that and look at it again. But previously, it was higher to the north, and it was pretty small. But it is higher to the north.
Yeah, I mean, and the second part of that was just thinking about the time period of analysis. Like it would. I'm not sure whether that would, if we could pinpoint a time over which the AMOC declined or which the circulation changed, maybe you get a more robust signal. Of course, it could work the opposite way too. I'm wondering if that you've looked at that sensitivity at all, or if you chose the time period for a particular reason.
We haven't looked at it too closely yet, but that is something we're going to do. The way the model is constructed, it takes a couple more steps to get back to the time series space from rate space.
Yeah, I remember a little bit about that model, not enough, but yeah. So okay, well that's it. I think it's a cool step forward with it. So thanks.
Yeah, I like this comment at the end here, the greater DC area. Yeah, that would be interesting to see. How much of the correlation?
Hi, Brett, thank you very much for your talk. That was very interesting. Yes, so you did make a distinction between coastal versus open ocean sea level rise and how much that contributes to the AMOC slowdown. So could, for example, the MoCA array and other transects that measure transport in the ocean support this distinction? Do you know of observational support for that?
There's. I think we kind of get into some problems in how we define the AMOC, right? So the coastal part of the AMOC is typically this deeper boundary current as well as part of the Gulf Stream. And then when we go into the open ocean, it's kind of this return flow, I think, from the south, from north to south. And so the rapid array, I think, I mean, they have a way of disentangling them, but I forget exactly how they do it.
Yes, I see. Yes, that is a very interesting question, actually, because at least the rapid group keeps saying that a lot of the high variability of the AMOC signal that they measure across the transect at 26 North near the coast comes from the the RC exchange effects. But so that would be interesting if that could be shown that it's sea level rise changes.
Oh, I see what you're saying. Yeah, that's something we should look at a little more as well. Yeah, there's a lot of stuff here that we've kind of just here. Let's start to think about it a little more, but it's going to take a while.
And I have another question too, which is kind of I'm wondering if you know whether ISAT and the JSON, the radar satellites have actually built simulators that we could use to perhaps explain the differences, applying simulators in the models and look at, for example, what are the differences between the estimates that they give.
That's interesting.
Do you know whether there are simulators for ISAT-2, for example?
I don't think so. I haven't come across any. I would think there should be. There are for SWAT, right? So I would guess they would have done this. But yeah, that is not something I've actually really thought about. So
okay. Yes, thank you. Thank you.
Okay. Any more questions? We're at the hour now, so.
We have one message. Thanks. Is there a way I can save this chat?
I think.
Save chat. Yeah.
Okay.
I think I got it.
Okay. Okay. Thanks a lot, Brett.
Okay. Thank you, everyone.